Welcome back! Do you remember that little module here with a little u-blox GPS module? So a module on a module. I made an extensive mailback video about that, card here, link in the description, where I actually connected that thing to an Arduino and got it up and running. Meanwhile, I made some improvement to my breadboard setup. So the most visual is that antenna platform where I fixed with some Velcro band the GPS antenna so it's no longer flipping in the breeze. Looks cute, doesn't it? And of course I cleaned up here the connecting wires on the breadboard. But the stuff the Arduino is receiving via the serial port from that u-blox thingy looks still, kinda gibberish. To be more exact, it looks like NMEA 0183 gibberish. So I thought I'd make a little video series about the NMEA, National Marine Electronics Association, Standard 0183 from 1983. It has been updated since then, so no worries. Which became also the IEC Standard 61162 Part 1 in 1995. That standard has 4 major sections. Number 3 hardware specification and number 4 data transmission within the IEC standard. That's number 5 and number 6 because IEC inserted 2 more chapters here, but just with formal stuff. Describe a connection between a talker and one or more listeners. To be more exact, an asynchronous unidirectional serial connection. Please note that serial connection is neither RS-232 nor RS-422. That's often stated there in the interweb, even in the Wikipedia, but it's wrong. In general, there's a lot of dangerously incomplete or outright wrong information about these standards out there. The reason being, these are copyrighted standards, and a copy of the NMEA 0183 sets you back $1,000 and a copy of the IEC equivalent a few $100. So not very many people have actual copies of these. Fortunate for you, I do have copies of these standards. I have the IEC 61162 Part 1 Edition 4 from 2010, and that's equivalent to the NMEA 0183 version 4.00, and I also have an original NMEA 0183 version 3.01 from 2002. I kinda feel the compulsion to make an overview video over all the NMEA standards and set the record straight, at least in some regards. We'll see. Don't get me wrong, there's also absolutely excellent information about the NMEA 0183 standard out there on the interweb. But you have to be careful. Some of that information, by the way, is even better than the stuff provided by the standard itself. Got a little bit carried away there, sorry. What I really want to talk about today and in some following videos is number 5, data format protocol, and number 6, data content within the IEC standards, numbers 7 and 8. And they define the sentences, that's the wording of the standard, that are transmitted from the talker to the listener. And why does the standard speak of talkers and listeners and sentences instead of, for example, transmitters, receivers, and messages? Well, your guess is as good as mine. I think it was 1983, Coke and LSD. I'm planning to do that by going through all the 150 pages of the standard, one by one, because I need you to feel my pain. Sorry. No, I plan to do that by taking small portions of the standard and condensing them down into conventional notations like syntax diagrams and regular expressions. Unfortunately, the notations and the language of the standard itself is absolutely one of a kind, let's say that. Remember 1983, Coke and LSD. And after each theory portion, I want to do a practical implementation using the GPS module up there and the Arduino up there. But we will not limit ourselves to GPS stuff because, yeah, let's face it, you get a lot of information about these GPS sentences out in the interweb. We also will do some compass sentences and maybe later on AIS sentences, so the automated information system, where chips exchange their positions, their courses, and their speeds. So let's start with the first page of theory then. As mentioned before, I will base everything on the ASCII Standard Edition 4.0 from November 2010, which is equivalent to the NMEA version 4.00. For those of you who have actually access to the standards, I have here everywhere in cursive lettering the ASCII chapter numbers of the chapters where I extracted the information from, so you can check if I'm really telling the truth. So let's start with the data format protocol and the character set being used. It's a 7-bit ASCII, so just from 0 to 127 decimal, and we have some reserved characters. Starting with a new line, and I'm using the C++ notation here, carriage return, exclamation mark, dollar, star, comma, backslash, tilde, circumflex, delete. Valid characters we can usually use go from space to circumflex, but without the reserved characters. All other characters are undefined and shall not be used. There's, however, an escape sequence that starts with a tilde, and that's followed by a 2-digit hexadecimal uppercase number expressing an 8-bit ASCII code. Next we have the sentences, and I'm skipping the chapter about fields here because it makes much more sense to talk about those later on when we understood what a sentence is. The general structure of a sentence looks like that. It starts with a dollar or an exclamation mark, so yeah, reserved character, and it ends with a carriage return new line, reserved character again, and sorry, first errata, that was of course \r, not \c. In between we have a maximum of 79 characters, and that brings the maximum length of a sentence to a total of 82 characters. Within this block we find an address field, 0 to n data fields, and that's not explicitly mentioned in the standard at that point, so it's in blue, usually a checksum field. Approved messages, and that's the wording of the standard, not mine, look something like this, and I'm using a syntax diagram here. So they start, of course, with a dollar or an exclamation mark, followed by an address field, and then come either 0 or n comma separated data fields. That's followed by a star, a checksum field, and our carriage return new line. The checksum is the XOR of all characters between the starting character and the star. Unfortunately, there are different classes, my wording, of approved sentences. Plus we have these proprietary sentences which look a bit different. So we are not quite ready to implement that. However, knowing the structure of the sentences is already helpful. So let's write some code for this. That's the code I'm currently running on my Arduino to display the data that comes from the GPS module on the Arduino serial monitor, and it's really just 4 lines of code. So I initialize the USB serial here to talk to the Arduino serial monitor, and I initialize the serial 1 so I can receive data from the GPS module. And then I wait until the USB serial is really connected and ready. And if that's the case, we go into the loop. And there I really just check if some data is available on the serial port from the GPS module. And if that's the case, I read 1 byte of that data and I write that byte to the USB serial port, so it's displayed on the Arduino serial monitor. Now, that's the code implementing what we've learned so far. So first I define an enum here, a sentence status, and if we have no sentence at all, it's none. And we are expecting on our serial port a $! On exclamation mark. And if we receive that, then our status is started and we can receive more characters until we receive a carriage return, in which case the sentence is terminated. It's not completed yet because we need to receive a new line too, and then the sentence is completed. I also define a constant here, an NMEA sentence max length 82 characters. The setup is exactly the same, we just initialize our serial ports. Then we get into the beef, our loop, and I declare here 3 static variables so their values survive each entry into the loop. First, of course, a char buffer with the NMEA sentence max length where we can store our message. Then the actual sentence length, which is initialized to 0, and then the sentence status, which is initialized to 1. And I also have a little buffer character variable here. Then comes a while loop that contains the main functionality. So first we check if data is available from our GPS module and if the sentence status is actually sentence is not completed. Then I read a character from my GPS module and then we go into a huge switch statement that switches according to the current status we are in. Our first case here is, of course, for sentence status none. And if we get a $! On exclamation mark, then that's our first character of our sentence, and our sentence length is set to 1, and our status switches to started. The next case is, of course, we already started with the sentence. And we add the next character simply to the sentence. Yeah, the length of the sentence is increased. If we receive a carriage return, we switch the status, of course, to terminated. Not completed, just terminated. We also check here if our current sentence length is already over our maximum sentence length -2. We leave the last 2 characters for the carriage return new line. In which case the sentence is invalid, so we reset the sentence length to 0 and the status to none. Finally, our last case is, of course, the terminated status, and we also append the next character to the sentence length increased, and if that character is indeed a new line, everything is fine and our status is completed. Otherwise, something was wrong again, and we reset the sentence length to 0 and the status to none. Please note, we do that continuously until we run out of data or our sentence status is actually completed. So we've read a complete message from the serial port. And then the rest of the loop is really trivial. So if after we read here a complete sentence, the status is completed, I do a 0 print sentence on the Arduino serial monitor and I write out all the characters in that sentence and then I'm finished with it. So I reset the sentence length and I set the status to none again, and our loop up here, our while loop, can start working again. or if we have run out of data and have to wait for the GPS receiver to send more over the serial port, then we simply do nothing here and we enter again our while loop. That's it. Now let's have a look how this looks on the serial monitor. And it looks like that. Not much different, admittedly. We have sentence in front of it now. But instead of an endless stream of characters, we now have each and every message neatly stored in a character array, and we can process it further. But we gained something else. If I now, cycle randomly the power of the GPS module, we would expect, let's stop that for a moment and scroll back. We would expect to see a lot of gibberish, but in fact we don't. The only gibberish we see is that line here and that line here, where you see we have here $, so two interleaving messages due to the power cuts, and here, and there's obviously a non-printable character, but otherwise we have absolutely no gibberish. And the rest, like these $, we could filter out too if we checked if a dollar is coming in between. And we can also add a timeout and stuff and whatnot. But for now, that should be good enough. While this code works very nice, it doesn't look very nice. It already devolves in some kind of spaghetti code, and we can't have that because we only covered 15 pages so far of the standard. So let's encapsulate everything we've done so far into some types and classes. And that looks something like that. So of course we keep our constant here for the maximum message length, but our character array and the length of the message is encapsulated inside a struct NMEA sentence. Then we have something that could be called an abstract class. I'm not using really the mechanisms for abstract classes here from C++. But anyway, that class has no functionality and just defines the interface for any NMEA listener we might want to implement in the future. So it has, of course, a protected member NMEA sentence and only two methods. So sentence available will return true when the listener has read a sentence. Here it always returns false because the class does nothing. And a second method, pull sentence, which will just return that sentence that has been read. Please note the sentence here, the member is initialized to an empty string and 0 length, just in case. And using that as a base class, we define our NMEA listener hardware serial, which encapsulates all the functionality we've written so far. Before we go here into the public method and constructors, let's have a short look at the private members. So we have here a pointer to an Arduino hardware serial object, could be anyone, it doesn't have to be serial one. And we find our num here again, not as a type def, I'm using that just inside that class, so a type def would be an overkill, but we have our enum sentence status here again. Now to the constructors. I delete that empty default constructor from the base class because we really need a hardware serial for that class to work. So that's this new constructor, and just to be on the safe side, I also call the constructor from the base class, and our member variable serial is set to the parameter serial, and our sentence status is set to none. And that's all what's happening inside this constructor. Now, The method Boolean sentence available contains the code we've already written. So we have still that buffer for our character, and then comes our big while loop. The only difference here is I'm no longer using the global serial1 object, but here my serial member variable, which is a pointer to a serial object. And yeah, here at that point, I'm of course no longer using the characters and the length variable, but that member struct. But everything else is exactly the same. So we come to our second and last method here in that class, and that's that pull sentence. And I have here a buffer variable for my current sentence, which is initialized, of course, to 0 length and an empty string. And if my sentence status is complete, then I copy my current complete sentence into that buffer, so I can safely set the length of my internal message to 0 and can reset the sentence status to 0, so we can receive a new message. And then I return the message I saved in that buffer. And that's it for the object encapsulating the functionality we've written so far. Of course, I have here one instance of that listener object, which I initialize with our serial1 Arduino object. Setup is unchanged, and then there's nothing much left in the loop. I have here one struct sentence, which I use for buffering reasons, and if the listener says there's a sentence available, then I pull that sentence from the listener, and that's the same. I print that sentence to the Arduino serial monitor. Of course, that code does exactly the same as the one before, just in a much nicer manner. Now, are you up for 2 more pages of theory? Then let's talk about fields, at least for now address and checksum fields. The general format of an address field is 1 or more digits and uppercase letters. And I'm using regular expressions for that stuff here. So yeah, that's our character range 0 to 9, A to Z, and a plus just means 1 or more. At this point, I want to introduce some symbols and abbreviations for stuff defined in the standard, otherwise my syntax diagrams get too crowded. The standard defines so-called talker identifiers inside the address fields, and these are exactly 2 characters of digits or uppercase letters. Ignore the blue stuff for the moment, and I will use a symbol, or respectively abbreviation, TI for them in my syntax diagrams. These talker identifiers are not hardware identifiers. I mean, they can't be with just 2 characters. Instead, they are identifying the semantics of a talker. For example, if a talker is delivering GPS position information or glasnost, that is the Russian GPS position information. Please note that one and the same talker hardware can use different talker identifiers in the sentences it sends out. Then we have sentence formatters inside the address fields, which are 3 characters, digits or uppercase letters. Please ignore again the blue stuff, and I'm using the abbreviation or symbol SF for them. The sentence formatters determine which kinds of data fields you find in a message. Finally, we have the manufacturer mnemonic codes inside address fields. These are 3 character, digits or uppercase letters, and of course they are identifying the manufacturer of the talker. And I'm using here the abbreviation MC. Now that we know the elements these address fields are made of, we can have a look at the 3 types of address fields the standard defines. First, we have approved address fields, and these are used for parametric and encapsulated sentences. Next page. Please note that approved sentences also include query sentences, but query sentences use query address fields. Now, an approved address field is made of a talker identifier followed by a sentence formatter. That's easy. So, second, query address fields. These are made of a talker identifier, another talker identifier, more about that when we look at the query sentences, followed by the letter Q. Time to double back to the blue part of the sentence formatters. So both approved and query address fields consist of 5 characters, and query address fields end with a Q. In fact, approved address fields, that is sentence formatters, never end with a Q, enabling you to distinguish between the two. The standard never explicitly says that, but if you go through all the sentence formatters defined in the standard, so from chapter 832 to 83109, you noticed its effect. So the better definition of a sentence formatter would be 2 characters, digit, uppercase letter, followed by a third character, digit A to P and R to Z, leaving out the Q. Finally, we have the proprietary address fields, which are of course for proprietary sentences, which are, according to the wording of the standard, not approved sentences. Anyway, they always start with a P, and that's followed by the 3-character manufacturer mnemonic code, and then the manufacturer is free to add 0 or more characters, 0 to 9 and uppercase A to Z behind that. Doubling back here now to the blue part of the talker identifier definition. So, proprietary address fields always start with the letter P. Fact is, talker identifiers never start with the letter P, allowing you to distinguish between approved and query address fields and proprietary address fields. That's actually explicitly stated in the standard, not in the chapter where they define the talker identifiers 72222, but further down in chapter 8.2 you find a table for a list of all valid talker identifiers, so a nice 2-character list, and suddenly you find a line with a single character P, which simply states, oh, that's proprietary. So the better definition for a talker identifier would be it starts with a character O to 9 and then uppercase A to O, leaving out the P, Q to Z, followed by a second character O to 9, uppercase A to Z. And then we have the checksum field, which is simply a 2-digit hexadecimal number, O to 9, A to F. We already saw that simply the XOR of all characters between the starting character and the star before the checksum. And I will be using CS for that. Now that we know the 3 types of address fields defined by the standard, we can actually talk about the 4 different classes of sentences defined by the standard. Classes being my terminology, the standard doesn't really have a word for that. Anyway, we have first the parametric messages. These make up the main body of all sentences defined by the standard. And they start with a $, followed by an approved address field, then 1 or more data fields, a star, checksum, and carriage return new line. The sentence formatter within the address field determines which data fields are contained in a sentence. Second, you have encapsulation messages, and at a first glance they look quite complicated. The use case is the following here. You want to transfer some binary data that simply doesn't fit into the 82 characters you have for a sentence. So you break up that binary data into several packages which you transfer in multiple sentences. So we're talking here about a multi-sentence message. The sentence formatter in the address field again determines what binary data you are transferring. They start with an exclamation mark followed by an approved address field, and then after a comma comes a field x1, which gives you the total number of sentences inside that multi-sentence message. After another comma we have a field x2, which gives you the sequential number of that message within all the messages that make up that multi-sentence message. After another comma follows the field x3, which together with our address field makes up a unique identifier for the whole multi-sentence message. Its purpose is to allow you to make sense of your x1 and x2 field in case you are transferring several multi-message sentences interleaving, that is in parallel. The standard doesn't mention it at that point, but this field is actually optional. So later on, and therefore here in blue, you see you can skip that field if the total number of sentences in your multi-sentence message is just one. This is followed by one or more data fields, which data fields again is determined by the sentence formatter in our address field. Comma, and then finally comes the binary data, another comma, and we have a field x4, the fill bit number. The binary data is of course encoded in ASCII characters, and each ASCII character there represents 6 bits. So the fill bit number gives you the number of bits in the last character that are just there to fill things up and don't have any meaning. Then we have start, checksum, carriage return new line. Third, we have the query sentences, which are much simpler. So their purpose is that a listener, which is talking here, can request a specific sentence from a talker, which is listening in that case. So they start with $, and then comes our query address field, and the first talker identifier here in that address field is the listener requesting a sentence, and the second talker identifier is the talker from which the sentence is requested. That's followed by a Q, comma, then the sentence formatter, that's of course the sentence we want to have from the talker, star, checksum, carriage return new line. In the beginning I mentioned that the hardware specification and the data transmission stuff in the standard just defines a unidirectional serial interface between talker and listeners. So to use these query sentences, a listener has to implement a second hardware talker interface, and a talker has to implement a second hardware listener interface. So we can send these query sentences via a second unidirectional serial line from the listener back to the talker. Finally, we have the proprietary sentences, which are, again, according to the wording of the standard, not approved sentences, but manufacturer specific. So they start with $, and then comes our proprietary address field that contains a P, the 3-letter manufacturer code, and then to the specification of the manufacturer 0 or more uppercase alphanumericals. And that's followed by the proprietary data, which can consist of all the valid characters plus a comma or a tilde. Then star, checksum, carriage return new line. Now, how can we distinguish in our code between these 4 sentence classes? It's easy for encapsulation because they are the only ones that start with an exclamation mark. But all others start with $. So let's have next a look at proprietary. There the second character is a P, so we're golden there, and that leaves us with parametric and query. And there we have to do something that's called in parsing or scanning a look ahead. We have to look at the 6th character in our sentence, which is for query a Q. And all others must be, by definition, parametric. So let's write some code and use what we've learned so far. And here it is. And we start off with a whole lot of type definitions just to make stuff more readable. So I have here three type definitions, just character arrays for my talker identifier, my sentence formatter, and my manufacturer code with the appropriate length. Then I have a enum address field type, which can be either invalid, just in case, approved, query, or proprietary. Next, we have three structs here for the different types of address fields. We have a struct for the approved address field, which of course contains a talker and a formatter. The query address field contains a listener and a talker, and the proprietary address field is a struct containing just the manufacturer code. Please note that the manufacturer-defined characters that might come after that are not included here because we don't know how many. Yes, I just inserted a C into manufacturers. Next, we have the NMEA address field, which starts with the type of the address field, and then comes a union with three members: an approved address field, a query address field, and the proprietary address field. The thing about unions is at any one time only one member of that union is active, and the union takes up only so much space as its biggest member. The C++ runtime decides by watching which member has been written last, which is the active member. Then we have another enum, the NMEA sentence type. That's what I called in the slides sentence class, but using the word class in C++ is a really bad idea, so I'm calling it type. We have invalid, just to be on the safe side again, then our parametric sentence type, encapsulation sentence type, query sentence type, and proprietary sentence type. Finally, we have our central struct NMEA data content. For now, it contains the sentence type and our address field. Much further down, behind the loop, we'll find a new function, NMEA decode, which gets as argument a constant reference to the sentence. We don't want to change that inside that function, and it returns our NMEA data content of that sentence. It has a buffer variable content, and then comes a big switch statement, which decides what kind, type, class our sentence actually is. So we first look at the first character of the sentence, and if that's an exclamation mark, then of course our type is encapsulation. And we derive our address for that sentence from another function further down, NMEA decode approved address. If it's $, we go into another switch here. And that looks at the second character of our sentence, and if that's a P, then of course our type is proprietary and our address is derived via the NMEA decode proprietary address function. Otherwise, we go into another switch statement and we look at the sixth character of our sentence. And if that's a Q, we have, of course, a query sentence, and otherwise it's a parametric sentence, and we derive the addresses by NMEA decode query address or NMEA decode approved address. If we fail to identify the sentence class type, we set it to NMEA sentence invalid. And then come the three functions for decoding the addresses. I will only explain the first one, NMEA decode approved address, in detail. So it gets as an argument, of course, we saw that already, a constant reference to sentence, and it returns an NMEA address field. It has a buffer variable address, and we are string copying the appropriate characters from our sentence into our talker and formatter string array. That makes approved, the union member, inside the address the active one. And then we set the type of the address to NMEA address field type approved, and we return the address. Same with NMEA decode query address. We are just using another member of that union and copying the characters. And with NMEA decode proprietary address, also just copying the characters here from the sentence into the appropriate member. I have two more helper functions here. That first one prints out the data content. It also gets a reference to a content struct. And depending on the content, it just prints out param, query, encap, or proprietary. And this is followed by a printout of the address field if we have a valid address type. And I'm using for that another helper function, NMEA print address field, which is down here. And yeah, depending on the type of the address field, it prints its content. That's it. Now let's have a look at the loop. And there we have a new buffer variable, content. We still have here our listener if statement. If a sentence is available, we get that sentence. But now we use the NMEA decode to decode that sentence into its content. We still print out the sentence, but right after that, we print out the NMEA data content. So let's have a look how this looks like in the serial monitor. And it looks good. Let's stop the auto scroll for a while. So we have here a sentence $GN_RMC, and it says that's a parametric message from the talker GN, and the formatter is RMC. GN_VTG, GN_VTG, and so on and so on. Oh, we have here other talkers, GP, GSV, and talker GL with a GSV. Tell you what, I'm cutting the power now to my GPS receiver, and we clear the whole thing and make a power startup. Stop the scroll and look what we get. Oh, here we get something else. So let's go through the talkers here. So we have talkers GN, GP, and GL. And we have, and then it starts again, and we have the sentence formatters, text, RMC, VTG, GSA, GSV, GLL, another text, then RMC, VTG, then it repeats itself. I guess we have our work cut out for the next time. This shall be enough for now. Yes, that was one of my longer videos again. But we covered a lot of ground and did a lot of groundwork for decoding NMEA sentences. And next time we will actually decode the NMEA, the parametric NMEA sentences we get from that GPS receiver. Till then, bye!